Hi there, I'm Estelle Trengove and this is my lecture on resistors in series and in parallel. Combining resistors in series and in parallel is one of the tools in the toolbox of electrical engineers that we use to make circuits more simple so that they are easier to analyze. In this lecture, we'll look at how we can combine resistors in series to get an equivalent resistance, and how we can combine resistors in parallel to get an equivalent resistance. And this gives us the general case. And then we'll also look at two special cases. So we'll look at the special case of resistors in series, which gives us a voltage divider, and also the special case of two resistors in parallel, which gives us a current divider. And remember that resistors in series and resistors in parallel just builds on knowledge that you already have. So it builds on Ohm's law. And remember that Ohm's law says that voltage is equal to current times resistance for a particular element. And it also builds on Kirchhoff's current law and on Kirchhoff's voltage law. Here we have a circuit with some resistors in series. So we've got resistor R1 with the voltage drop V1 across it. Resistor R2 with the voltage drop V2 across it. And this circuit goes on and on. We could have an infinite number of resistors in series up till the resistor Rn, which has a voltage drop Vn across it. And from Ohm's law, remember, we know that in this circuit, V1 is equal to I R1. V2 is equal to I R2. And so on up to Vn, which is equal to I Rn. And of course, you'll know that all of these currents I flowing through all these different resistors is the same current I. So if we now use Kirchhoff's voltage law around this closed loop, so by Kirchhoff's voltage law around the loop, we see that there's only one source and a whole lot of resistors. So we know that all those resistors are absorbing power, and so we know that by the conservation of energy, the source Vs must be supplying the power for all of those resistors. So by Kirchhoff's voltage law, we know that Vs is equal to V1 plus V2 plus, and so on up to Vn for however many resistors there are that are connected in series. Now if we take, let's call this set of equations 1, and we'll call this equation 2. So if we substitute 1 into 2, then we get that Vs is equal to I R1 plus I R2 plus, and so on up to plus I Rn. And because all these I's are the same, so it's the same current I flowing through all of the resistors. So therefore, we can write this as Vs is equal to I times R1 plus R2 plus, and so on up to Rn. And now you can see that for resistors in series, R equivalent is just simply equal to the sum of all the resistances. So it's equal to R1 plus R2 plus, and so on up to Rn. And that is the general case for resistors in series. In this circuit, we have a whole lot of resistors in parallel. So we've got R1 with voltage V1 across it, R2, and so on up to Rn. And here again, we're assuming that the circuit could go on infinitely with an infinite number of resistors. And so, because if we apply Kirchhoff's voltage law to each of these loops, we can see that in this case, Vs is equal to V1, Vs is equal to the voltage across R2, and Vs is equal to the voltage across resistor Rn. From Ohm's law, we know that current is equal to voltage over resistance. So therefore, for this circuit, we know that I1 is equal to Vs over R1, I2. So remember that this current I flows into this expanded node, and it splits into all different currents running through each of the resistors. So I2 is equal to Vs over R2, because remember we said because these elements are all in parallel with the voltage source, the voltage across each resistor is Vs, and so on for an infinite number of resistors in parallel up to In, which is equal to Vs over Rn. And then we know at that expanded node by Kirchhoff's current law, we know that the current I is equal to I1 plus I2 plus, and so on up to In. And now we're going to take these equations, so let's call them equations 1, and this is equation 2, and if we put 1 into 2, then we get I is equal to Vs upon R1 plus Vs upon R2 plus, and so on up to Vs upon Rn. And because the Vs is the same in each case, we can therefore say that I is equal to Vs times 1 upon R1 plus 1 upon R2 plus, and so on up to 1 upon Rn. And so for resistors in series, for resistors in parallel rather, we can model these resistors in parallel as an equivalent resistor, which is 1 upon R equivalent and that is equal to 1 upon R1 plus 1 upon R2 plus, and so on up to 1 upon Rn. And this is the general case for resistors in parallel. A voltage divider is a special case of resistors in series. So, and for a voltage divider, we just have two resistors in series, and this combination comes up so often that it's worthwhile committing the formula to memory. So we can see by Ohm's law in this case, V1 is equal to IR1 and V2 is equal to IR2. By Kirchhoff's voltage law, around this closed loop, we know that Vs is equal to V1 plus V2. And so putting 1 into 2, we see therefore that Vs is equal to IR1 plus IR2 which is equal to IR1 plus R2. Therefore, we can say that I is equal to Vs divided by R1 plus R2. And let's call this equation 3. And now we're going to put equation 3 into equations 1. And that gives us V1 is equal to Vs over R1 plus R2 times R1. And V2 is equal to Vs over R1 plus R2 times R2. So we can write it like this. V1 is equal to Vs times R1 over R1 plus R2, and V2 is equal to Vs times R2 over R1 plus R2. And so you can see now that they both have Vs in common and also R1 plus R2. And the only difference between them is here the combination is multiplied by R1, and here the combination is multiplied by R2. So in fact, you can see in a voltage divider, therefore, V1 is proportional to its own resistor, R1, and V2 is proportional to R2. So if we want to make V2 bigger, for example, we just have to put in a bigger resistor into the combination. I don't want this video to get too long, so in the next video I'll do the current divider and then also an example, a worked example of resistors in series and resistors in parallel. This is the end of this video.